Okay, so we are now looking at our third video, our third part of this topic, and in this case we're starting to look at logarithms. So what we need to know about logarithms is that they are essentially just indices. So when we're talking about these, it is still an index, so therefore it relates together with our exponential equations. This equivalency is something you need to be aware of. So if we're having a look here, we have an exponential equation. A is the base, n is the power, the index, and it's equal to n. When we're rearranging this, when we're rewriting it as a log equation, the base is still the same, which is a. The index is now equivalent to the log, and what was equivalent to the index expression is now written here within the log. So we do need to know how to do this. So if I'm trying to write 10 squared equals 100 as a log equation, we will have log, the base here, which is 10. What I had that was equivalent to my index expression moves into the brackets here, and it's equal to the old power that we had before. So this is something that we're going to use a few times as we go along. Similarly to what we were looking at with our exponential functions, we also have a whole lot of rules for how we can multiply, divide, add, subtract logarithmic expressions. So these are our log laws, or our laws of logarithms. I'm going to go through and prove them all, like I did last time. Once again, you don't need to know how to prove these, so if you're interested, feel free to keep watching. If you're not, then you can fast forward until we get to the examples. So to start with, what we're going to do is we're going to try to prove this first law. So I'm going to let log base A of m equal x and log base A of n equal y. I need to rewrite both of these as exponential equations. So our base here was a, so our base of the exponential equation will be a. It was equal to x, so x becomes our power, and then it's going to be equal to m. Similarly here, a is our base, so a is still our base. Because it's equal to y, this becomes our new power, and it's going to be equal to n. We're going to use this as we go through and prove all of our different log laws. So the first thing we're going to do is we're going to consider what happens if we have m multiplied by n. So when I'm multiplying these two things together, we multiply a to the power of x times a to the power of y. Remember that when we are multiplying indices where we've got the same base, we add the powers. So we get mn equals a to the power of x plus y. We can now rewrite this as a log equation using our formula that we had before. So if we take log of the base, our base here was a, so our base here is going to be a as well. In brackets we have what it was equivalent to before, mn, and it's now going to be equal to our old power, x plus y. We know x was defined earlier as being equal to log a of m, and y was defined as log a of n earlier. So we've proven, therefore this has proven the first of the logarithm laws. We can prove the second one in a very similar way, and you might like to try this one for yourself. But we do it the very similar way. This time we consider what happens when I divide m divided by n. So that means I'd be taking a to the power of x divided by a to the power of y. Again, we know when we divide, we subtract the powers, so it would give me a to the power of x minus y. Now we need to convert this to a logarithm equation, so once again we take log of the base, which is a, so our base is here. Inside our brackets have what our equation was equal to before, and now it's going to be equal to the old power of the exponential equation. We know x was defined up here as being log a of m, so instead of x we will get log a of n, minus, instead of y, we have log a of n. And this has proven our second of the logarithm laws. We we then continue on. Now we're considering what happens when we have powers. So the next one we're proving here has our powers. So we defined log a of m as being equal to x. So this time, let's see what happens if we take m and raise it to the power of p. Well, we know that m is equal to a to the power of x. That's what we had there. And we're going to raise this to the power of p. We know that when we have powers, we multiply the indices, giving me a to the power of x times p. Okay? Now, the next thing we need to do is to convert this exponential equation into a log equation, similar to what we did the first two times. So this will become log, our base here was a, so our base here will be a of m to the power of p from what we have here, and it's going to be equal to our old power, which was xp. Now, because we know that x is equal to log a of m, we can substitute this expression here into our equation here for x. I'm going to write p first, just because that's what we're aiming for here when we're trying to prove it. Remember, multiplication is commutative. X times p is the same as p times x. So we would get p, and then instead of x, we're substituting log a of m. So this now has proven our third log law. Moving on, our next one. Now our fourth log law is very similar to our third one, so we don't need to do too much proving of it, because if I'm trying to prove this, well, we should all know that anything, when I have 1 over a variable, it is same as having that variable to the power of -1, okay? Using our previous log law 3, we know that when we've got powers, they can be written in front of the log. They can be multiplied by the log. So I'm going to write that -1 is now multiplied by log a of n, which is proving the fourth logarithm law. We've got 2 left to look at. So we're now going to prove that log a of a is equal to 1. So what we're going to look at to start with this, if we consider what happens when I have a to the power of 0 equals 1. So we're starting with a to the power of 0 equals 1 in this case. What we can do now is we can convert this to our log law. So if I'm converting this, what we're going to get, and I actually think now I might be proving the other one. Anyway, if we're converting this one here, what we get is log of base a of 1. Whoops, sorry, I'm proving our next one. Oh well, proving them out of order. Log base a of 1 is going to be equal to 0. So this is proving our final log law, that anything log of 1 is always equal to 0, regardless of the base. If we take the fact that a to the power of 1 equals a, because remember, whenever it's not written, the power is 1. If we convert this to a log equation, we take log, our base is a, so this is our base. This is what we're going for here. This is our base, so this a part is what we're getting here. In our brackets, we get whatever our equation was equal to, which was this a. So this a from here is moving in here, and it's equal to the old power. So we know that whenever I have the matching base and the argument, part of the brackets there, it's going to be equal to 1. Okay, so I think that we're ready to do some examples. Please note as well, logs are only defined for positive expressions. We'll get into that a bit more and explain why once we get a look at the graphs. But whatever is inside this logarithm, it must be positive. Not 0, not negative. Alright, when we're asked to evaluate something, this means we need to work out the answer. We need to work out a numerical answer. Now, first of all, let me say I'm sorry, I've typed something incorrectly on your worksheet. So can you please cross this one out, what it should be, because as it was written, we're not going to be able to simplify it nicely. So let's instead do this for log base 4 of 0.25. Sorry, I missed the 2 in your worksheet initially. If we're working this out, we need to see what we can do, how we can use our log laws. Well, 0.25 is the same as 1 over 4. Hopefully we can all agree to that. We can also say that's the same as 4 to the power of negative 1. 1 over 4 is the same as 4 to the power of negative 1. Then what we can do is we can take this power and we can write it in front using our third log law, or our fourth one. So we get negative 1 multiplied by log base 4 of 4. Now we know log base 4 of 4 is equal to 1, so I'm getting negative 1 times 1, I'm getting an answer of negative 1. If we are evaluating the next one here, we need to, again, we've got a base of 9 and we've got 27 here. To be able to evaluate, to be able to work out a numerical value when we don't have a calculator, we have to look at 9 and 27 and be able to do something with those two things together. So log base 9, well, 1 on 27, that's the same as 1 over 3 to the power of 3. Doesn't really help us, but perhaps we're getting somewhere. Then we can say, okay, well, this is the same as 3 to the power of negative 3. But what we're still wanting, if this is a base of 9, I want to somehow make a 9 here so that we can cancel out, so that we can use the same thing. Log base 4 of 4 equals 1. I want to get the same thing here. I want to have log base 9 of 9. Well, we know that we can turn a 3 into a 9 if we square it. So I'm wanting to square this whole thing. I can't just square it though, but I can raise it to the power of 2 over 2. That's like raising it to the power of 1. It's not actually changing anything. If we rearrange this, again, remember multiplication is commutative. So this is the same as saying, so what I had here, if we're thinking about this little power here was giving me negative 3 times 2 over 2. That's the same as saying negative 3 times 2 over 2. That's the same as saying 2 times negative 3 over 2. Negative 3 times 2 is the same as 2 times negative 3. That's the same as saying 2 times negative 3 over 2, because it's commutative. So what I'm going to get is a 2. This is the same as saying 3 to the power of 2 to the power of negative 3, I've moved out there, over 2 was our part there. So it's still the same expression. Regardless, all of these, they're all equal to negative 3. Doesn't matter how we write them, they're all equal to negative 3. These two are still, expressions are still equal. This means that we're going to get our power, negative 3 over 2, can be written in front of our log. We then have log base 9 of 3 squared is 9. Now we have log base 9 of 9 is equal to 1, and we get our answer of negative 3 on 2. Let's continue on, and now we're going to look at simplifying logs. So when we're simplifying, we're not now expecting you to get a numerical answer, we're just trying to write this in a more simple format. We have a rule, our second log law says that when we're subtracting one log minus another, what we end up doing there is that we divide the arguments. So we'll have log base 3 of 54 divided by 18. We can work out what 54 divided by 18 is. It gives us 3, and then we know log base 3 of 3 equals 1. In this case, it did evaluate, it did simplify down to give us a numerical value. That's not always the case. Bear in mind, this whole thing, this is still a number. Logs of a number are a number, okay? These are still numbers. It's just that sometimes we can simplify to give us whole number values or rational numbers. Sometimes we can't simplify, we can't remove that log in any way. One other thing to mention before I forget, please make sure you are always writing brackets for logs. You must always put whatever is inside here within the brackets. So please keep that in mind when you're working through your exercises, when we're doing SACs, when we're doing past exam questions, and when we're doing the actual exam. Next one, okay, we have log base e, 3 multiplied by e to the power of 5x. When it's not written, there is a multiplication sign in between the 3 and the e. So we can separate this into two separate logs using our first log law. So this is equal to log base e of 3 plus log base e of e to the power of 5x. Now, log base e of 3, we can't work out what that is, not without a calculator. Like I said, it is a number, but we can't work out what it is. Here I've got a power. What can we do with our powers? We can take them and write them in front of our expression. So we get 5x log base e of e. Now luckily for us, once again, when we've got the same base and the same argument here, it's equal to 1, so that will cancel out. And it leaves me with the final expression that we were looking for. Our last example for today. Okay, so this was from a past exam. As I've mentioned to you before, in almost every tech-free exam, there is either a logs or an exponential question requiring you to solve an equation of some kind without a calculator. Sometimes the log or exponential question might involve inverses instead, but quite often it's solving an equation of some kind. So this is something we do need to know how to do, and you do need to know how to do without a calculator. So we're wanting to solve this equation. We need to be able to cancel out our logs. We're trying to solve for x. It's too hard to do at the moment because we've got log base e everywhere. We need to find some way of cancelling that out. So what we need to do is to group everything on the left side together so that it is just one term, one logarithm term. To start with, what we can do, we've got a 2 here. That can be written as a power. So we get log base e of x plus 2 squared minus log base e of x equals log base e of 2x plus 1. Now, our second log law, when we're subtracting, that means we can divide the arguments here. So we would get log base e of x plus 2 squared over x. Remember, we've got everything inside brackets, equals log base e of 2x plus 1. Please be very careful when you're writing log base e. It needs to be an e. We need to be clear that this is a subscript. We're writing log base e. We're not writing loge, okay? Be very clear, log base e, not loge. Yes? No. Okay, now, because we've got log base e on the left and log base e on the right, they can cancel out. Because our bases of the logs are the same, that means whatever is within them, the expressions within must also be equal. So I would then get x plus 2 squared over x equals 2x plus 1. We're going to continue trying to solve this. If I were you, I would pause the video right now and try this myself. Otherwise, if you're wanting to keep watching, we can multiply. I want to move this x, so I'm going to multiply both sides by x. That would give me 2x squared plus x. At the same time, I'm going to expand this bracket here, which would give me x squared plus 4x plus 4. This is now quite a straightforward equation to solve. It's something you would have been expected to solve in year 10. You should be able to do this without too many problems. I need to collect all of the terms to one side so that I can use the null factor law. So I can subtract x squared, that would give me x squared. I can subtract 4x, so that would give me minus 3x. I can subtract 4, so I've got minus 4, and it's now equal to 0. I now need to factorize this. So factorizing, our factors of 4 are 4 and 1. I need to multiply to give negative 4, add to give negative 3, so I'd have a negative and a plus. This means x is equal to negative 1 or x is equal to 4. Now, similar to what we were doing for our exponential equations, this is not necessarily the final answer. I need to consider if these values actually make sense for the expressions I had earlier. So we need to try to substitute these into our expressions and see what's going on. if I was to substitute negative 1 into this expression here, I would get negative 1 plus 2, I would get positive 1. That's okay, that's fine. If I was to substitute negative 1 in here where the x is, that's not okay. Remember, we can only have logs of positive numbers. If I was to substitute negative 1 in there, this number is no longer defined. Remember, log base e of a number, this is just a number, and log base e of negative 1 does not exist. So that means this solution does not exist. So we can say as x must be greater than 0, okay, it must be positive, x does not equal negative 1. Similar again to exponential equations, we need to give a reason for why this does or does not happen. Sorry about that, everyone. Finally, looking at this, x equals 4. If I put 4 in here, 4 plus 2 is 6, so that is fine. Substituting 4 in here, that's positive as well, so that's fine. So our final answer is x equals 4. And that's it for how to simplify logarithmic expressions. We'll go on to sketching logarithms in the next section.